Welcome to the Math Record. Today we'll be learning how to find derivatives of trigonometric functions, their inverse functions, exponential functions, and logarithmic functions. This video will cover part 3 of chapter 2 in our calculus class. Okay, let's begin. In our previous video, we introduced the rules of derivatives and applied them to polynomial functions. Now we will use the same concepts to find the derivatives of these new 4 types of functions. Okay, let's start with trigonometric functions first. There are only 2 derivatives you need to know for trigonometric functions, one for sine of x and the other for cosine of x. Then we could use these derivatives to find derivatives of the other 4 trigonometric functions using derivative rules. Okay, first up, sine of x. So we have sine of x. The derivative of sine of x is cosine of x. And for cosine of x, the derivative of cosine of x is negative sine of x. Okay, for now, we'll just have you memorize it. If you want to know more, there is a link in the description where you can learn how to prove this. Okay, so using this idea, we could use this to find tangent of x, cosecant of x, secant of x, and cotangent of x and their derivatives. So basically, let's start with tangent of x. So how do you find tangent of x? Well, remember, tangent of x is just sine of x divided by cosine of x. So, do you see what we do here? If we want to find the derivative of tangent of x, we just need to find the derivative of sine of x divided by cosine of x. So we just have to use the quotient rule of derivatives, which is basically the derivative of the top. So derivative of sine of x is cosine of x times the original functions on the denominator, which is cosine of x, minus the original function of the top, which is sine of x, times the derivative of the denominator. So the derivative of cosine of x is negative sine of x. So we have negative sine of x. Sorry about that. So negative sine of x. And this is all divided by the denominator squared. This just uses the quotient rule of derivatives. If you want to find more about it, you could check out our previous video, which talked about the rules for derivatives. Okay, so let's simplify this. We have cosine of x times cosine of x, which is just cosine of 2x, right? Cosine squared of 2x. And then we have minus sine of x times negative sine of x. So the negative here and the negative here just makes a positive. So that's just plus sine of 2x. This looks familiar, doesn't it? Well, this is just a trigonometric identity for the Pythagorean version. So cosine squared of x plus sine squared of x is just 1, which is just a trigonometric identity. So using that idea, we just keep this here for a while, and we just need to put in the denominator, which is cosine of 2x. So we don't have to do anything to the denominator for now. Okay, so as I said before, cosine squared of x plus sine squared of x is 1. And then cosine of cosine of x squared. So the inverse of cosine is secant, so this is just, so the derivative of tangent of x is just secant squared of x. So secant of x to the power of 2, basically. So that's the derivative of tangent. So that is the first of the 4. So we cover tan. Now we just need to cover cosecant, secant, and cotangent. For these type of trig derivatives, the only ones you need to memorize is sine and cosine. If you want to find tangent, cosecant, secant, and cotangent, you could just use the rules that I'm going to show now. So you could just derive it later on. But the most important is sine and cosine. Those that are the fundamental trig identities that you need to know. Okay, let's start with let's begin with cosecant of x now. I'll rewrite the sine of x. So derivative, sorry about that. Derivative of sine of x is equal to cosine of x. And the derivative of cosine of x is equal to negative sine of x. Okay, just know these, just memorize these, and you'll be fine. It's not that difficult. Basically, sine and cosine and negative sign. So, to think about this, you can always just remember it graphically. So let's say you have sine of x, right? Yeah, sine of x looks something like this. Sorry, my picture is not the best, but basically it's like this. So, if we want to find the derivative of this, we basically just need to find the slope, right? Slope at each point. So let's just choose like some random points to find the slope at. So let's find the slope at here. This is supposed to be a 0. I'm sorry, I'm bad at drawing. So the slope at here is like, we have something like this, right? It continues on. So if we choose a slope at the middle, it kind of looks like it has a slope of 1. So let's just say it has a slope of 1. I'm not going to prove why it has a slope of 1, but it is a slope of 1. So basically we have a slope of 1. And now let's keep going. So as it goes up, right, it slows down until that slope reaches 0 right here, right? So at that point, we have slope that's slowing down until it reaches 0. And then it goes negative, right? It keeps going negative as it goes down until it reaches this point. I'm sorry, the graph bad, which is just negative 1. Because if this is positive 1, then this has to be negative 1. Right? So it goes down, but increases into negative, like get this curve into a negative 1 at that point right there. Okay? And then it gets less negative, right? Until it goes back to 0, right? Right here at 0. So it kind of has another curve until it goes to this point, which is 0. So you see, because at this point is 0, so at this point has to be 0 right here. So if you kind of see this graph, it kind of repeats again and again and again. So if you kind of ignore that graph on the bottom, let's just try this in a different color. I'm sorry I've been using white. So let's try red. Okay. So we have a point like this, and we have something like this, and then we have a point right here and here, right? And then you basically repeat that function again, and oh, sorry about that. Right here. Sorry about that. And then there's a 0 here. So if you kind of just look at this graph, doesn't just this look like cosine of x? If this continues on and on and on, right? Basically, that's just cosine of x. So you could, if you understand how the sine of x works, you kind of just derive cosine of x. We're not going to prove it, but using some kind of logic, that kind of makes sense. So that's for cosine of x. Now let's look, that's for sine of x, to get the derivative of sine of x to get cosine of x. Now let's try something to get cosine of x. Okay, so cosine of x, we're going to do the same method. So the cosine of x is like this. Right? So it begins at the top and then kind of has this curve. It's basically the same as sine, but it's kind of shifted a little bit over. So we have a derivative of sine. So we started here. This is the maximum point. I'm sorry if I drew it off. So the maximum point here is 0, right? So we have 0. The derivative of that is at 0. Okay? So starting from 0, it kind of goes down and down and down and down, right? So it kind of goes negative until it reaches this point right here, which is negative 1. So right here is negative 1, so it kind of keeps getting more negative. And it's kind of a curve because this is a curve, right? And now as it gets more negative, it has negative, 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 and it goes to this point. And this point is at 0, right? Because the slope has right here that only goes to that point has to be, like at this point, has to be a straight line that that is parallel to the x-axis, so it has to be 0. Same concept, it's like the similar concept that we use for sine of x. So at this point it has to be 0. And then you have to keep going until you reach this point, which is 1, right? Because if this is negative 1, then this has to be 1. Okay, so this is at 1. And it gets positive until it reaches 0, right? So it kind of goes to a curve until it reaches 0. So at this point it reaches 0. So it kind of looks like this, right? And then you could just keep on going and going, right? And if you test more points out, you kind of see that it kind of looks like a sine of x, but a sine of x looks like this, right? This kind of looks like the opposite of that. So you kind of just have to, I mean, not opposite, but like flipped over the x-axis. So since it's flipped over, that means whatever version that's positive has to be negative, and whatever is like positive has to be negative, right? So flip to the bottom, and whatever is negative has to flip to positive. So it has to be just multiplied by negative, so it makes negative sine of x. And that's how you prove how these trigs work. You could do it with other proofs using limits, but for this class, we won't be teaching that. For now, you just need to understand that the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. And you could just use the intuition that I showed a few seconds before to understand how it works. Now let's go back to cosecant of x. So if we want to find the derivative of cosecant of x, we just need to find out what cosine of x equal to. So cosecant of x is just 1 over sine, right? 1 over sine of x. So we need to find the derivative of 1 over sine of x. So we just use the quotient rule again. So for all these like trig functions, we just use the quotient rule, because tangent, cosecant, secant, and cotangent, tangent and then cotangent, basically they're all quotients of in some relationship of sine of x to cosine of x, or it's vice versa, basically. So we could basically just use these these ratios to like get and use the quotient rule to find the derivative of the other 4 trig functions. So for cosecant of x, we have 1 over sine of x. So the derivative of the numerator is 0. Multiplied by the denominator, which is sine of x, minus, right, the numerator, which is 1, times the derivative of the denominator. So derivative of sine of x is cosine of x, all over the denominator squared, which is sine x squared. So 0 times sine of x is just 0, and this would just be negative cosine. So on the top is just negative cosine. Sorry about that. Negative cosine of x divided by sine of x squared. Right? So if you could leave it like this, but if you want to simplify it, basically we just need to find out what this is. So cosine of x divided by just one of the sine of x's. So the regular trig function for tangent is just sine over cosine. Since this is cosine over sine, this means this has to be cotangent. So this is negative. Don't forget the negative. Negative cotangent of x, right? And then we're still left with a sine of x on the bottom. So 1 over sine of x is just cosecant of x. So this would just be cosecant of x. So the derivative of cosecant of x is equal to the negative cotangent of x times cosecant of x again, which is a little strange, but it kind of works. But it works for the graph. So this is how you technically prove it. Now we just did cosecant of x. Now let's try secant of x. So we have sine of x. The derivative is equal to cosine of x, right? I rewrite this so then we don't forget. And then that's cosine of x is negative sine of x. Derivative of it. Now let's try secant of x. So basically we do the same point of what we did last time, which is basically just 1 over the ratio. So secant of x is just 1 over cosine. Derivative, right? So the derivative of 1 is 0. Times the original of the denominator, which is cosine of x, minus the numerator, which is 1, times the derivative of the denominator. The derivative of cosine of x is negative sine of x, all divided by the denominator squared, which is cosine of x squared, right? So 0 times cosine of x, that's just 0. So all we have left is just negative 1 times negative sine of x. So negative times the negative is just positive. So we have sine of x all over cosine of x squared, right? So sine divided by one of the cosines is tangent. Okay, and then we're just left with the cosine on the bottom. One more cosine on the bottom. So 1 over cosine is just secant. So you can leave it like this, or you can simplify to this, basically. So the derivative of secant of x is tangent of x times secant of x, which is, it does seem like it has a similar concept to how cosecant of x derivative is equal to negative cotangent of x times its original function again, right? So it kind of looks the same, right? So we have a negative and we have a cotangent of x and then times the same function. For secant, we have tangent of x, like the reciprocal of cotangent of x, without that negative, and then multiplied by its same function. So it kind of looks like I have a similar idea. And that's usually how I remember it. But you really don't have to. As I said before, you just need to remember the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. And then you could just use the quotient rule to derive the other four. And now the last one, which is cotangent of x. So let's rewrite this again. So sine of x, the derivative is cosine of x. And cosine of x, the derivative of cosine of x is negative sine of x, right? So cotangent of x, the derivative. So tangent was sine over cosine, and cotangent is the reciprocal of that. So this one is cosine x over sine of x. And that's usually how I remember cotangent and tangent. So we need to find derivative of this. So the derivative of the numerator, derivative of cosine of x is negative sine of x, right? And now we need to multiply by the denominator, which is sine of x, minus the numerator, which is cosine of x, times the derivative of the denominator, which is sine of x. So derivative of sine of x is cosine of x. So we're just using the product rule over and over again to prove these. So sine of x squared on the bottom, right? So this is the quotient rule all over again. So we have negative sine of x squared, right? And then negative cosine x squared divided by sine x squared. Sorry if I'm writing it like differently both times, but they're basically the same thing. So sine squared of x and sine x, and then I put parentheses and then the squared. Both are the same thing. It's just that I like to write it differently, usually, but they're basically the same. So if we distribute out the -1, it's basically just sine of x plus cosine of x, right? So sine of x plus cosine of x is the same thing as 1, as I said before, for tangent of x. So we have a negative for that, so it's just -1. So negative sine of x, sine squared of x minus cosine squared of x is just -1. So sine x squared, we just leave as that. So sine x squared. So the reciprocal of sine is cosecant, right? So since it's squared, it has to be cosecant squared of x. And that's how we get the derivative of cotangent of x. So the derivative of cotangent of x is just negative cosecant x squared, basically. So if you remember, like a few minutes ago, we proved that tangent of x, the derivative of tangent of x, right, was equal to secant of x squared. Oh, sorry about that. Sorry, I have kind of bad handwriting. So we have the derivative of tangent of x is equal to secant squared of x, and we have the derivative of cotangent of x is equal to negative cosecant of x. You see how they're kind of similar? They have this squared, but then one of them has a negative and one doesn't. And this one is just 1 over a cosine, and this is just 1 over sine. So it has the same idea of how we did it for secant of x and cosecant of x. They have these really similar similarities. And that's just because of how sine of x and cosine of x derivatives kind of work out. So that basically covers everything for the trigonometric functions and their derivatives. As I said before, for these 6 type of trig functions, you only need to memorize the sine of x and the cosine of x. So for the other 4, you could just use the quotient rule. So let's use these ideas to like try out some examples. So let's say you want to find the derivative of like sine of x plus cosine of x, and then the derivative at, I don't know, pi over 2. Sorry, pi over 2. So as I said before, x, you cannot use degrees. So for calculus, you cannot use degrees. You're always using radians. Because radians are using numbers in relationship to the circumference of a circle. Trig functions uses a circle, basically, right? So we have a circle, and basically we have trig functions that like just go around and then test out that circle. And then we use that circumference to find the radians. Degrees are just an arbitrary number that was used, which is 360, just because it could divide to a lot of numbers. So that's why we can't use degrees for calculus, because it's not a real thing that we could use. But radians we could use. So for radians, so whenever you see a number is in radians. So usually a radian goes from 0 to 2 pi, because that's the circumference of a unit circle. So a unit circle is a circle with radius 1. So the circumference is just 2 pi radius. So radius is 1, so the circumference is 2 pi, right? So it's from 0 to 2 pi. So if you ever see anything higher than 2 pi, that means just looping around. So if 2 pi is pi is about like 3.14, so 2 pi is like 6.28. So if you see something like 7, right? We have a unit circle. We say we have 2 pi. So we have a unit circle. It goes around in loops. So it goes 1 time. So that's 6.28 length about. And then if you want to go 7, basically you're just doing this, looping around, and then 1 more. So it goes like a little extra right here, right? And that's why we have that 7. So if you ever see something higher than like 2 pi or like 6.28, then basically you have something higher than 1 like cycle of a circle. It's not something you really need to know, but usually you're gonna use your calculator for this. But if you don't want to do like a bunch of like the really big math, so you have something like 7, you could just subtract the 2 pi away, or like the multiple of 2 pi's. Like if you have like 15, then you could subtract like 2 like 4 pi radians away, basically, because it's like 2 pi radians. Anyway, let's get back here. So sine of x plus cosine of x derivative at pi over 2. So derivatives, we could just use the regular sine rules. So you could always follow the regular sine rules. Just because they're trig functions doesn't mean they're any different. They're a different type of functions, but they have to follow the same rules. So when you're adding derivatives, all you need to do is just separate the equations and then do the derivative of those and add them back together. So they're the same thing. So derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. So it's just negative minus sine of x, right? So the derivative of sine of x plus cosine of x is just cosine of x minus sine of x. It's really just that simple. And you need to find the derivative at pi over 2. So you just need to plug in pi over 2 into x. So cosine of pi over 2 is 0. Sine of pi over 2 is 1. So that's minus 1. So the derivative of sine of x plus cosine of x at pi over 2 is just negative 1. So the slope at pi over 2 is basically just negative 1. It's basically just that simple. Okay? Now let's try another one. Let's now have something with like products, okay? So we have sine of x, right? Times maybe a dot times tangent of x, right? And then we find the derivative of that at like, let's say, at pi, you know? So when you're doing the product, yeah, since you're multiplying sine of x times tangent x, we need to use the product rule for derivatives. So it's the derivative of the first one times the normal function of the second one plus the normal function of the first one times the derivative of the second one. So let's just do that. So the derivative of sine of x is cosine of x, right? And the derivative of tangent of x, you don't need to know this now. So if you want to prove it, you could just split tangent of x into sine of x divided by cosine of x, and then do the derivative of this using the quotient rule. But for now, I'm just gonna write it out for you so we save time. So the derivative of tangent of x is secant squared of x, right? And let's keep going. So we have the regular function of sine times sorry, we had to I messed up a bit. So derivative of sine, and then you leave the second one the same, so tangent of x. And then plus the regular function, which is sine of x, times that derivative. So this one is the secant squared x. I'm sorry about that. And now we just need to multiply. You could multiply these together, but sometimes you just don't have to. So you could kind of just split them out. So usually, when I see something with like tangent or like cosecant, secant, and cotangent, I like to split them back up to their sine and cosine because I know how to do sine and cosine the best. So tangent is sine over cosine. So this thing is just sine x, and then there's and then this is just cosine times that cosine on the bottom. Kind of this, tangent of x is sine of x over cosine of x. So this tangent, this cosine multiplied by this cosine on the bottom just makes just cancel each other's out. So all you have left is sine of x. And now you have sine of x plus secant squared of x. So we have sine of x. Secant squared of x is just cosine squared x, right? So we can't cancel anything of that out, basically. So let's try like actually doing the math on this now. So sine of pi, just plug in pi into x. So sine of pi is 0. And sine of x, so you put the pi in there, which is 0. And then cosine, you just, basically this is the same thing as saying cosine x squared, right? So cosine of pi is 1, and then, -1, so -1 squared is just 1. So we have 0 plus 0 over 1. So 0 divided by any number is just 0. Unless that number is 0, then which you could use calculus, which we will teach later on. But for now, we just have a 0 divided by a number is basically just 0. So 0 plus 0 is 0. So basically, the derivative of sine of x times tangent of x at pi is 0. So the slope has to be, like whatever the curve is like this. Sorry, it's kind of bad. But it has a slope of 0, basically. That's your general idea. Okay, so that was our second example. Let's try like one more example. But this time, instead of multiplying, which uses the quotient rule, and like if you want to use the quotient rule, you could. So we did the adding first, and then we did multiplying. Now let's try something with chaining. So let's try like sine of x. Sine of cosine of x. So we do something a little bit more simple. So derivative, and let's do that at like pi over 3. Pi over 3 radians. So usually, just to note, this is not anything with the question, but basically, if they say something like 2 radians, right? This is not the same thing as saying 2 pi radians. 2 pi radians actually means going 1 complete cycle. 2 radians is not the same thing as 2 pi radians. So this only goes by like 2. And pi, right, is 3.14. So this is like 6.28. So 2 is like a third of 6, about a third of 6.28. So this only goes about a third of a circle. So remember that. Don't think this is 1 complete cycle. So that's just to note. Usually that's some kind of a common mistake. So you really can't do that. But if you have a calculator, it usually fixes that by itself. So you don't really need to like think too much about it. But if you're doing by hand, it's good for you to know. So for chain rule, you always just have to chain because you have a cosine instead of a sine. So remember how we did chain rule? It's outside in. So basically, the derivative of sine is cosine. So whatever is cosine of x, right? So whatever is still inside, just substitute that into the variable. So we have cosine of x, so the variable is x. So we just need to substitute cosine of x into x. So we just have cosine of x, right? So this is our first function, first a chain. So we just need to do the derivative of what's still left inside. So the derivative of cosine of x is sine of x. I mean negative sine of x, right? And then we don't have anything inside cosine of x. There's still x, but derivative of x is just 1, basically. So we just have this. So the derivative of sine of cosine of x is cosine of cosine of x times sine of negative sine of x. So you kind of have these two cosine, a cosine inside a cosine. And now we just need to put pi over 3 inside. So you could do this with a calculator, but it's not going to turn out into a pleasant number. So cosine of pi over 3 would be like 1/2, right? So using your calculator, cosine of pi over 3 is 1/2. So you have cosine of 1/2 multiplied by negative sine of pi over 3. So we have negative 0.866, all right? So let's just use 3 like decimal places and we'd be fine. So cosine of 1/2 is about 0.878 rounded, and then we have negative 0.866, right? So we kind of just have to multiply them together. So multiplying that together, we have about, sorry about that. We have about, we'll just use the equal sign. It's approximately, try to use approximately if I can't draw. So we have negative 0.76 approximately for our slope. So the slope at sine of cosine of x, the derivative at pi over 3, is negative 0.76 approximately using your calculator. So that basically covers the examples for trigonometric functions. So for everything I just shown, basically you only need to know sine of x and cosine of x as a reminder, basically. And then you could just use the normal derivative rules. Now let's try getting the inverse trig functions. So instead of using the quotient rule, we need to use the chain rule and apply some trigonometric ideas. So first we need to understand the idea of how inverse works. So when you plug in a inverse function with this normal function, you basically get like whatever you input it as your output. So what does that mean? So let's say we have like a function like y, right? Y of x. Then actually, no, let's actually use the proper notation. Let's use f of x, right? Same thing, is I just don't want to use y. So the inverse of f is, right, f of negative 1 is how we learned in school, basically. So let me erase that part. So the idea is that, let's say you plug in a into x, right? So we say x is equal to a and plug that in. So we have f of a is our output, right? Because that's what it's going to equal to. So basically, if you put f into a into this x, then f of this number, which is equal to a, right? Because the inverse function, the inverse function is that they switch the x values and the y values. So whatever's the x values for f of x, it will become the y values for the inverse of x. And then whatever's the like f of a, right? Whatever is the values for the output of f of x will become the inputs for negative 1 of x. So why do I explain all that? Well, basically, there is a general equation of how this works. So if we have an equation called f of x, right? And we have its inverse, which is f of negative 1 of x, at the inverse of f. Basically, we could say that f of negative 1 of x So f of negative the inverse of f inside f is the inverse of f is inside f. So if you plug those in together, the output is equal to x. That's true, right? Because if you plug in a number and you in the inverse, and then you do the inverse of that, basically that inverse is basically just x. Because if you plug in a number and you do some operation to it, and then you do the reverse operation to it, when you just get the same number again, and that's the idea of what inverses are. So this is true. And we could also and the opposite case also works. So we could just use the inverse of f, and you put f inside is also equal to x. And you could also use this idea. But for our case, we would just need to use 1, so let's just use this one. F of -1 of x is equal to x. So if we could use an equation like this, we could use the chain rule to find out basically the inverse derivatives of that function. So if we want to find the inverse trig, we'll just need to apply this idea. So let's say we want to find the inverse of sine of x, right? So we want to find the inverse of this. We want to find this derivative. So basically, we have sine, inverse sine, right? F, and then inverse of f is x. Inverse of f is negative sine of x is equal to x, right? I basically just plugged in our equations in the right place. So this normal equation, and then the inverse inside that normal equation is equal to x. So let's chain this. So if we don't find the derivative of this, we need to do the derivative of the left side, and then we need to do the derivative of the right side. Because when we do a derivative of like some kind of equation, we basically had to do the derivative on both sides all the time. So let's work with the left side first. So the derivative of sine is cosine. And then whatever is still inside the equation, you just plug it back in. So yes, sine and -1 of x. That's just the idea of chain rule. So as you do more of it, you'll get better at it. And then, right? And then you basically multiply this equation times whatever is still the inside, which is the derivative of sine of x. So sine of x and derivative of that. So now you have this idea of sine of -1 of x. I mean inverse sine of x. I keep using -1, but it's sorry if I keep doing that, but basically it's the same idea. So we have the inverse sine of x is equal to basically now we just need to do the derivative on the right side. So the derivative of x is just 1, right? So now we have this equation right here, and this part is equal to the inverse sine of x that we are trying to find. So we just need to reverse our equations to understand. So now we just need to find what this equals to, and then get it to the other side, and then we basically just get this equation. So how does this work? Basically, when you do inverse trig functions and you want to find their derivatives, you have to understand how triangles work. So trig is just some kind of application with triangles. So let's just understand like how this works with like an actual picture. So let's say we have a triangle, right? A trig is always a right triangle. So sine of x, x is just kind of a number. Usually this is why I don't like to use x, because x does not mean like the x coordinate. I'm using x as a ratio, so sorry because it's the wrong notation. Usually when they write they write sine of theta or like cosine of theta. Theta just stands for like the radian measure, so I'm sorry for that, but for this case we'll just use x for now. So x is just a usual variable, and that's why I use it. So, but it's bad examples. But let's just actually start doing this. So inverse sine of x, right? So that means this number x is the ratio of because sine is the opposite over the hypotenuse, right? So x is just opposite over hypotenuse. That's the ratio because the inverse sine of x will just get the angle measure, which we'll denote right now as theta. So the inverse would just be, let's say, call this x. So opposite over hypotenuse. So this is x over 1. This x divided by 1 is just x. So this has to be true. So inverse sine of -1 of x is just the same thing as this picture. So basically, we could use this idea to find out what this entire thing stands for. Now, as I said before, the inverse sine of x is equal to theta. So cosine of theta right? That simplifies the cosine of theta because theta is equal to inverse sine of x. It's basically just adjacent over hypotenuse, right? So now we have to find this side length in relation to this side length. So since this is a right triangle, right, we could use the Pythagorean Theorem, which is just this side length squared times plus this side length squared is equal to this side length squared. So basically, it's just this side length, which is equal to 1 minus x squared, right? Because square root of this side is just 1 minus x squared. Square root of x, square of x is just x squared. And then add them together is 1. And then 1 squared is just 1, right? So that's equal to 1, right? So this is true. So this follows the Pythagorean theorem. So we have this as our formula. So cosine of theta, right? Because we know theta is equal to inverse sine of x. Then basically it's just a square root of 1 over x. So this entire thing right here, using this picture, which you could logically think about, is equal to just square root 1 minus x squared, right? This is cosine of theta is just adjacent divided by hypotenuse. So square root 1 minus x squared divided by 1 is just square root 1 minus x squared. So then multiply by the inverse sine of x, right? Inverse sine of x, its derivative is equal to that 1. And now we could just find it. We could just reverse the equation. So sine, the inverse sine of x, it's the derivative of the inverse sine of x. It's just 1 divided by that number, which is divided by square root 1 minus x squared. And that's basically how you find the derivative of a inverse trig function. You just do this idea. And we're going to use this idea to basically derive more inverse functions for a future video. So for like any function where we do its derivative, where we can't actually get an explicit like number that we have to do. So if we ever want to find like a derivative of inverse at a point, we really don't need to find its entire equation. We just need to find the derivative of the original function and then kind of reverse equations like how we did here to find its actual derivative. But we'll cover that in a future video and not here. For now, we're just going to be learning about the inverse trig functions. So the inverse of sine of x, the derivative of it, is 1 over the square root of 1 minus x squared. And that was just for sine. So let's try another example. Now let's just try it with cosine. So we have cosine, the inverse of cosine of x, and its derivative. We want to find this. So apply the same concept. So cosine of the inverse cosine of negative 1, right, of x is equal to x. So let's chain this again. So the derivative on the left side is derivative of cosine of negative sine of x. So plug in whatever is still inside the x. So cosine of negative 1 of x, right? And now this idea, we're going to have to multiply. I'm just putting the parentheses so we don't think it's cosine of negative 1 times the function, then take the sine of that. So just for notation. So the derivative of inverse cosine of x, that's what we're trying to look for. So cosine of negative 1 of x is its derivative. So we basically want to find this, so we just need to reverse this side. We need to get this to the other side. So we're just going to use the same idea. So the derivative of x on the right side is just 1. It's always 1, basically. So now we just need to draw a picture again. So this time, we have theta. We always have this as theta. And now we have a cosine of the inverse cosine of x. So the ratio, cosine is basically the ratio of the adjacent over the hypotenuse. So it's this side length over this side length, right? So the ratio is x, because this is inverse. An inverse trig. So the ratio is here is x to 1 now. Now basically, we need to find sine, right? Because this thing, as we got inverse of x to 1, is basically getting this angle, which is theta. So this entire thing is theta, as we did before for sine. So sine of theta is basically this side length over this side length. Don't forget the negative, we need the negative. So using that idea, use the Pythagorean theorem again, because this is always a right triangle. So 1 squared minus x squared, and then square root. So the opposite side, the side length, is just square root 1 minus x squared. Now, the sine of theta, right, because inverse cosine of x is theta, then basically sine of theta is equal to opposite over hypotenuse, so square root 1 minus x squared divided by 1 is just square root 1 minus x squared, right? So this entire thing kind of just simplifies out to negative square root 1 minus x squared times the inverse cosine of x, cosine x derivative, right, is equal to 1. So you kind of just reverse the equation. So we have the inverse of cosine of x, the derivative of that is equal to just 1 all over divided by the divided by the negative square root of 1 minus x squared. Right? So we just put the negative on top, and then we just put the square root on the bottom. Right? You can put the square root on you can put the negative on the bottom if you want, but you really don't have. But if you want proper notation, just put the negative on top. And that's how, if you ever search for like inverse like derivatives on Google, basically this is what you get, and this is how you basically prove it. And this is like one proof of how to do it, basically. Usually the method I use to think about it in chain rules, and then using like a picture. And this is the inverse cosine of negative x. So the inverse cosine, the derivative of the inverse cosine is equal to negative 1 divided by the square root of 1 minus x squared. Okay. So we're just gonna try like one more example with tangent of x. I'm not gonna be trying like cosecant of x, secant of x, and cotangent of x. You could try it. It's just the same idea, but I'll just try tangent of x to show you how ratios work. So we have tangent of tangent of negative 1 of x, right? The inverse tangent. And then we have that equal to x, right? Because, this is always true for a reciprocal, the general idea. Now we chain it. So the derivative of tan, as I said before, you don't have to memorize it, but I'll just show it now because it's faster. So the derivative of tangent of x is secant squared of x. Sorry about that. So secant squared of x. So x is tangent of negative 1 of x. Right? So let's put all these in a parentheses. And then you have to multiply whatever is still in the parentheses because you're chaining it. So this is the first chain. So our second chain is negative inverse tan of x. So the derivative of inverse tan of x is all we have left. Right? So we just need to reverse this entire equation to the other side. And then basically we could get the inverse tan of x. The derivative of the inverse tan of x. So that was the left side. So the right side is 1. As I said, derivative of x is always 1. Now let's just draw a picture again. So we have theta. This is a right triangle, always. Always theta in a right triangle. Theta, I'm just using theta. You could use any single like variable you want, but usually theta is the conventional sense. So inverse tan of x, tangent of x is sine over cosine. So that's just opposite over adjacent. So it's this side over this side, basically. So they're saying that the ratio is x. So let's just use 1, right? Because x divided by 1 is just x. So this is the correct ratio. And now we could use the Pythagorean Theorem to get the hypotenuse, which is just x squared plus 1, right? Because x squared plus 1 squared is just x squared plus 1. And then you square root that to get the hypotenuse. So you have square root x squared plus 1. And then the inverse tangent of x gets theta, right? As we did before for sine and cosine. So secant squared of a theta, right? We will just get secant is just 1. It's just basically the hypotenuse over the adjacent, right? Because cosine is just is the opposite, is the adjacent over the hypotenuse. So secant is the inverse of that, is the reciprocal of that. So secant squared of x is equal to the hypotenuse, which is square root x squared plus 1, all over the adjacent, which is 1, right? And then basically, don't forget the squared because this is secant squared, so you square the side. So since it's just divided by 1, it's basically just this equation. And now we square it, so now you just take out the square root, so now you just have x squared plus 1, right? So using that idea, we could just have x squared plus 1 is equal to basically this entire thing, using this picture as what we did before for sine and cosine, and then multiplied by the inverse tan of x, the derivative of it, is equal to 1. So the inverse, so the derivative of the inverse tangent is equal to 1 divided by the square, 1 divided by x squared plus 1. And that's the derivative for the inverse tangent of x, which is basically the same idea how it works. So all you want to do, if you want to do for cosecant, secant, and cotangent, if you want to find those equations, you basically just do the same idea. But they have some special properties of how it works because you don't understand how the domain and range for like cosecant and like secant and cotangent tangents work in relationship, because sometimes they might be taken out, because that's why whenever you look for Google and you see some absolute values on these equations, it's because, like, let's say you have a parabola, right? And you want to find its inverse function will look something like this, right? But you can't have like this bottom portion, because then it's not going to become a function, because it does not pass the vertical line test, right? Because you can't just plug in like a number right here and then you get this output and this output. So they usually just take out this bottom portion, you just get this portion that's left. And that's why they're talking about a restriction on the domain and range, and that's why they have those absolute values. So then you only get like a specific number. And that's basically the idea for the inverse trigonometric functions. If you want to do the rest, you could just search it up online, but I'll provide a link below for you to check it out if you want. Okay, now let's move on to the other part of this video, which is with the exponentials and the derivative of exponentials and logarithmetics. So let's start with exponentials. So let's just start with the general rule, which is basically, let's say we have a base number a, right? The power of x. If we want to find the derivative of that, that's basically just equal to that equation, a to the power of x, times the natural log of a. So natural log of a will be a constant then. So I'm not going to prove this now. If you want to find more, it's in the link below. I'm sorry if a lot of them are in the link below if you want to search out. But this is basically a general equation that's true. So let's just try an example with this. Let's say we have y is equal to like 2 times 3 to the power of 5x, you know? So the exponent is 5x, the base is 3, and we have 2 as this beginning value. So let's do the derivative of this. So when we do a derivative of y, right? Basically, a constant always stays the same. So we just have the 2. So basically, we have this. You always got to chain, because this is supposed to be 3 to the power x, but now it's 3 to the power of 5x, right? So you have to chain it. So even if it's to an exponent, you always have to chain. So we have 3 to the power of x. So the derivative of a exponential, because it's 3 to the power of 5x, is 3. And then we do the derivative of 3 to the power of x, basically. Derivative of this, which is just basically the same equation. So 3 is a, so 3 to the power x. And then ln a, so this is ln of 3. So we have the derivative of this is ln of 3 times 3. And then whatever's still left inside, you got to plug it in back to x, right? So you have x, you plug in the 5x back into x. You have 5x. And then you have to do the derivative of what's inside. You just need to multiply it. You don't multiply it here, you multiply it outside. So the derivative of 5x is just 5, right? This is just a regular polynomial. So the derivative of this exponent is equal to 2 times ln of 3 times 3 to the power of 5x times that 5. So you could just simplify this as 10 times ln of 3, because 5 times 2 is 10, times 3 to the power of 5x. So you basically just learn how to chain, basically. So you just need to learn how to chain the 5x here, which is not very that difficult, but if you want to, as I said before, just put the 2 down, do the derivative of 3 to the power of 5x. So we have 5x, which you have to chain in. So then the derivative of 3 to the power of x, ignore the 5x. Let's just say 5x is equal to u, right? So we have 3 to u. So we have derivative of 3 to u is basically ln of a. So a is 3, so ln is 3. And then you just keep the regular equation, which is 3u. So plug in 5x back into u, right? Into u here. So then you have 3 to the power of 5x. And then you have to do the derivative of u, right? To make 5. To get that 5. And then you multiply them out to get this equation, which is basically just that simple. And that's like another way if you want to like do like a chain rule, which is just substituting with like numbers and how it works. So an example would be like, this is off topic, but basically this would be how you do it. So we have like cosine. Since we're learning like trig and stuff, let's just try it with cosine. So let's do the same thing like cosine of sine of x, right? So we want to find the derivative of this, right? So basically, let's just say u is equal to sine of x, right? Let's just substitute. It does, even if you substitute, it's not that much different. So we have cosine of u, right? And u is just sine of x. So we just do the derivative of this first, and then we do the derivative inside. So the derivative of cosine of x is equal to negative sine of x, right? And I mean, derivative of cosine of u is equal to negative sine of u. So just plug in u back inside. So you have negative sine of sine of x, right? But then that's not all. You have to do the derivative of u. So derivative of sine of x is equal to like cosine of x, right? So the derivative of cosine of sine of x is equal to negative sine of sine of x times cosine of x. Sorry if it's not on the same line. I just kind of ran out of room. And you could just basically do the same thing twice. So even if you have like another one in here, like let's say that's not x, let's say that's like another cosine of x. So you have cosine of sine of cosine of x. Basically, you could say u is equal to cosine of a sine of cosine of x, and then you could say a is equal to like cosine of x, right? So you could just do the derivative of u, sine of u, and then you get this equation, and then you plug in this back into u, and then you have to do the derivative of this equation, right? Of u, and then you basically plug in a into this equation, so you get this into a, and then plug in a back into that side, like how we did with this, and then do the derivative of that cosine. And it's basically just a substitution method. It's the same idea, but if you want to just use substitution, it works the same way. So just make sure it's correct. So now going back into like exponents. So how do we do exponents? Like an actual exponent that's like natural. So there is like two kind of exponents. It's basically just the same idea, but let's say we have something like 5 of x. This is what we have as like a usually like compounding. I don't know what the exact term is, but basically it's just 5 to the power x. And then there's something called e, right? E is like then continuous. So to x. E is just a number, so it's just 2.178 or something, etc. Basically is to the power of x. So it's basically the same number. It's basically the same idea, but now it's just a different number, but this number is written as a symbol. So when you have to write this as a derivative, it's actually really simple. So remember the original derivative of a to the power of x is equal to a to the power of x times ln of a, right? So if we have e to the x, we just substitute e into a. So e to the x, and then times ln of a is equal to e. So ln of e, isn't that just the same thing as 1? So basically the derivative of e to x is equal to ea. I mean e to the power of x. So basically the derivative of a continuous like exponential is basically just like a continuous. So it's basically a really cool case of like having the derivative of a function equal to the same thing as like its original function. And e of x is like a really special case for that. So we're not going to try any examples with that because it's really self-explanatory. So let's just move on to like logarithmic derivatives. Now for the general case for this one, we have log of a, right, of x if we want to find the derivative of this, it's basically equal to 1 over x times ln of a. If you want to find the proof, it's in the link below. So I'll also like prove this here if you want me to, which is just the same idea of how how we did for inverse, but because log of a is basically the inverse of a exponential. So how we do this is that, let's say we have a times log of a of x, right? Because if it's a and it's log of a, this would just equal to x, right? Because if you do some kind of operation to x and then you do that inverse operation to x, then basically of that output, we just get back the original number, which is just x. And that's how inverses work all the time. So basically, we could just do the derivative and we just follow the rules. So the derivative of an exponential, which we just covered like a few seconds ago, basically is just a to the same equation, so a to log a of x, right, times basically the derivative of the inside, which is log a of x. So log a of x derivative. And then derivative of this side is just 1. Sorry, I forgot to multiply by ln and a. So multiply by ln and a. Because for exponents. Because derivative of a log ax. So derivative of a would just be derivative of a to log ax times its natural log. I forgot that for the exponential. So we have this. So log a. So a times to the power of log a of x times log a of x, the derivative of that, times ln a is equal to 1. So basically, you have this thing simplifies to x. So this entire side would just be x times ln of a times the derivative of log a of x derivative is equal to 1. And then you just have 1, get this to the other side, so it's just 1 divided by x times ln of a is equal to log a of x, which is what we just got here, right? So, and that's basically just how you prove it. So I think the link below also uses the same idea. So if you ever want to know, just use the idea of like inverses, and that's how you get it. So let's try an example. Let's say we have y is equal to like log I don't know, 3 of 2x. No. So the derivative of a log is just 1 over x times ln and a, right? So basically, let's substitute that in. So ln of x. So since our x is 2x, right? Because let's say this is u. So this x would be a u. So we just need to substitute that u in, which is just 2x, right? So whatever you have as a variable here, you just basically just plug it in. And then we just need to chain it. So we have 2x times ln of a. So ln of a. So a is the bottom portion, which is the 3. So we have 3. So we have 1 over 2x times ln of 3, right? And then we have to chain. So whenever you chain, you always multiply by the equation. You don't do like anything that's like really specific. Like you have to multiply like to the a here or like to the x here or something. No, you always multiply it to whatever that you get for your first derivative. So that's why it's called chaining, because you're chaining to your first chain. So your second chain would be the 2x, because normally it's supposed to be an x, but now it's 2x. So the derivative of 2x is just 2, right? So this 2 cancels out with this 2, right? So you just have 1 over x times ln of 3, which is basically just that simple. So the derivative of log 3 of 2x is just 1 over x times ln of 3. And that's generally how you always do it for the logs. So as we did before for e to the x for exponentials, now we're going to do natural log for the logs. So we have natural log is ln, right? Ln of x. The derivative of ln of x is just 1 over x. So how do we know that's true? Well, basically, you could just use that general idea of logs. So if we have log of a of x, the derivative of this, right, as we said before, is 1 over x times ln of a. Now, ln of x, this is the same thing as saying log e of x. So, because log e would just be natural log. So that's just basically the definition for ln. So if a is equal to e, right, then basically log e, which is ln of x, the derivative, is equal to x, same thing, you don't change anything about that, times ln of a, or a was e, right? So ln of e, the same idea, it's just 1. So this is just 1. So this is just 1 over x, which is what we proved is up here. And that's the idea of how, it's like the similar idea how we did for e of x, because ln of e is just equal to 1, or e to the power of ln, anything is just basically that output. And that's just the definition of how natural logs work. And that's like a really simple way to prove it. So that basically covers everything for like trigonometric and inverse trigonometric, exponential and logarithmic derivatives. For this video, we did not prove like how we got the derivative for like sine of x and cosine of x and exponential functions, even if we did do them like numbers for it. If you wanted to learn more to do, how to do it, as I said before, in like various times in the video, there's a link at the bottom of the video that shows proof for a variety of these equations. So you want to just check it out. So from this video, most of these derivatives you could just get using derivatives rules, as I shown before, like how we could just, for like the trig functions where we just use like derivative rule for adding, for subtracting, for multiplying, for dividing, and for chaining, right? But from this video, the only thing that you really need to memorize is that the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of an exponential function, like a to the power of x, is equal to a to the power of x times ln of a. So I'll just write it again. So you just need to memorize sine. The derivative of sine of x is equal to cosine of x. You need to memorize cosine of x. The derivative is equal to negative sine of x. And you need to know the derivative of a to the x is equal to a to x times ln of a, right? So, sorry if that was a to the power of x, and then you still multiply by ln and a. Not multiplying ln a to x to the a to the power of x. And then and then the log of a to the x is equal to 1 over x times ln of a. So these are the only 4 that you need to memorize. So generally, you just need, for the trig functions, you only need to know the sine and cosine. So any of the tangent, cotangent, secant, cosecant, those you could just derive using like trig rules. A to x, you just want to memorize this. It's just the most useful like formula to know if you're doing exponentials. And then you could just derive a bunch of formulas using this in the chain rule, basically. And then you have a log a of x, which you could just which you just need to memorize also, because then you could use this to like derive the same ideas like how you did with the exponentials with the chain rule. So that basically covers everything for this video. Thanks for watching, and I'll see you at the next math record.